Transformers. This be point number 5. Transformers are used to step up or step down voltage or current. I feel like I kind of said that. So are used to step up or step down voltage or current. All right, the ratio of EMF in the primary to the EMF in the secondary, EMF is what? Electromotive force or electron moving force. The ratio of the EMF to primary, EMF to the secondary is equal to the ratio of the number of turns in the primary to the number of turns in the secondary. This will all make perfect sense to you. So the ratio of the EMF, electromotive force, in the primary to the EMF in the secondary is equal to the ratio of the number of turns in the primary to the number of turns in the secondary. Example, which will make much more sense. If the primary has 100 turns, everybody knows what a turn is? Yeah, it's once around the block there. Once 100 turns. And the secondary has 200 turns. The EMF in the secondary will be twice as much as the primary. So the formula is this. E of P divided by E of S. So what do we have there? Voltage of the primary, voltage of the secondary is equal to the number of turns in the primary over the number of turns in the secondary. So if we looked at, I can put this over here. So EP equals voltage in the primary. ES is voltage in the secondary. NP is number of turns in the primary, and NS is number of turns in the secondary. All right, so far in everything we've learned, or should have learned, you've found that you cannot create power from nothing. Right? For example, you can't add resistance to get more current flow. You can't create some sort of magic where Ohm's law doesn't really exist anymore, where you can lower the voltage but increase the amperage, right? It just doesn't work that way. So there's number one, there's no free lunch. And number two, you can't really create something from nothing. So transformers keep that law going. Be nice if it wasn't that way. You know, you could plug something into your house and suddenly you're not paying electricity anymore.
What do you mean by no free lunch?
And somebody has to pay for everything. Well, in your situation, you probably get a lot of free lunches because you live at home.
I don't know about that.
You don't know you live at home?
Well, no, I know about that. Yeah. I cook for myself, though.
Okay. Who buys that food that you cook?
I actually do.
Okay.
At least the stuff I make.
Keep in mind that a transformer, a transformer cannot create power.
Is it D or C? Sorry. Okay.
Cannot create power. So,
Sorry, hey.
Powerful.
Apparently that was a transformer.
if the voltage goes up, I should put goes up in the secondary, because that's what we're talking about, in the secondary. In the secondary, the current must come down. So what I'm talking about here is if you have power, your power is 1 watt in the primary, guess what you're going to get in the secondary? Assuming it was 100% efficient, and it's not. But if it was, you get 1 watt in the secondary. You can't have 1 watt running through the primary and 5 in the secondary. That won't work. Now, thankfully, we're just going to look at stuff that's 100% efficient, but you got to realize it's not. So you got 1 watt in the primary, you're going to have point something in the secondary. So that means that Ohm's law is going to apply. If the voltage goes up in the secondary, the current has to come down because the power isn't going to change. It's going to be equal. So, all right. Now, in a transformer, glad I said that. In a transformer that is 100% efficient, and most are about 90 to 98% efficient. So says my source. Amperage in the primary is inversely proportional to the amperage in the secondary. So here's my formula. Here's your formula too now. So we had this one, EP divided by S is equal to I of S over I of P. Now notice that it crosses. So the P is over here and the P is down here. What other formula do we have that dealt with that? If you go way back to week 1. The gears. Remember the gears were inverse? So you got to swap that. So EP, ES, IS, IP. So you got to make sure you have that. So if we put this kind of all together, I've got turns in the primary over turns in the secondary can be equal to the voltage in the primary over the voltage in the secondary, which is current of which one? Secondary, right on, over current primary. And that goes back to the first one we had where it was EP over ES is equal to NP over NS. That's putting all of these together. Six. Let you guys get caught up. How we doing, Eric?
I'm good.
All right, you good?
Good.
So if a primary has fewer windings, than a secondary, it is a step-up transformer. If a primary has more than the secondary, than a secondary, it is a step down transformer. And of course a step down will do what to the voltage? What will the step down do to the voltage? Increase or decrease?
Increase.
Does what? I couldn't make it out. Decrease. Will decrease the what? Voltage. So we can see here we're always talking about step up or step down, which is relative to the voltage. Will decrease the voltage, but what to the current? Yep, increase. Increase current. The formulas are the same. It doesn't change whether it's a step up or step down. That's where you figure out the formula. So here we go. So power must, so remember, all right, if you don't know this, then you're not remembering, you're just learning it. Okay. That power in must equal power out. Of course, that's assuming it's 100% efficient, which it's not. So equal power in must equal power out. Assuming 100% efficiency, which it's not. But we can work that. So, comma, as voltage goes up, current must come down. I'll put that here. If voltage goes down, current must do what? Go up. Go up. All right, here we go. Ready to put it in. Question. All right, so a primary has 150 turns, and the secondary has 300. 300 turns. Input is 120 volts AC, and the output has a 100 ohm load. What does that look like? You guys figuring it out okay? You want me to walk you through it?
Yes, I'd like you to walk.
Thank you. Eric's awake. All right, so obviously first thing I did is I made a drawing. I like visual representations. And I filled in everything I could. Well, really all I know, there's 150 turns here and 300 here. I know that, oops, this is 100 ohms. And that's, I think, about all I got here, right? Okay, so I need at least two things to find the third. I don't know my current flow. I don't know the resistance over here. I don't know the power over here. I don't know the voltage over here, the current, nothing. So what I would like to find out, which makes the most sense to me right now, is probably to find this voltage right here. Okay, because we just know how this works. So using the formula, turns of primary over turns of secondary equals voltage of primary over voltage of secondary. I can fill that in. Turns of the primary is 150. Turns of secondary is 300. My voltage on the primary is 120, so I just solve for X. So cross multiply, I have 150X equals 3,600.
Or 30,
You sure?
sorry, 36,000.
Oh, now he's just throwing out numbers, so 36,000. Divide both sides by 150 to get rid of that. 150. So X equals 240. Now,
Do we have to do all that to, if we know, like you said in the previous, right,
well, I was just going to say, take a step.
I was like, couldn't we just do 120, 240
Yes.
volts?
Take a step back and look at it. You have 150 on one side and 300 on the other. So if the ratio is the same, we have a 1 to 2. So we can just go 1, 240 times 2. If you can see it, that's fine.
Okay,
Yep.
as you guys throwing these numbers out, I was lost for a second.
But what are you going to do if it's 150 turns and 14,000? Then you're like, yeah, I don't see that one. So you got to know how to do it because that's kind of how it works, actually. So, all right, so 240. So now I can get my current, which is 2.4 amps. And my power is 576 watts?
Yep.
Okay, so can I transfer the 2.4 over here?
Nope.
Why not?
It's not the same.
It's not the same. What is the same?
Watts.
576 watts. So now using that, which is PIE, I want to know the I, so it's P, power, 576 divided by 120 should equal 4.8, which is twice that, 4.8 amps. So 120 to 140, basically because it's a 2-to-1 ratio, there's twice as many in the primary as there is in the secondary. This is really times 2 this way and times 2 that way, and this is equal.
So the wattage stays the same throughout the transformer.
That's the power. The power stays the same. Now, if I want to be mean, I'd say in a circuit that is 95% efficient, well, then you would have to multiply 576 times 95% because it would drop down, and so this 576 would be less because you have power losses, which is true. But I don't think that you don't need to do that. So
You don't think?
it's not on the test.
Okay.
The FA doesn't ask you, so let's leave it at that. Okay. You can, but I don't care. Wasn't the question.
Put an R on there.
Yeah, you put an R there. So.
I know it's because I would do everything, but you can solve it if you want.
26 ohms.
6,
26.
26 ohms. There you go.
25.
25. It's 25 ohms.
Yeah.
Okay. It's all right. I didn't care, and you were awful close.
So confident.
Okay.
Confidence is key.
There. That's all I got to say about that.
In videos?
Vidges.
Bitches.
Trying to figure out when the right time is. Not yet.
What?
Okay.
Up somewhere.
All right. So the next thing we're going to talk about can be a little difficult to digest. And these are diodes and how they actually work.
Is it still technically an AC?
Not really. Diode, because do diodes work in DC?
Yes.
So it's just diodes.
Anodes and cathodes are diodes.
What's that?
Are we learning about anodes and cathodes?
Not really. I told you I'm not going to do anodes and cathodes. You don't need to. So,
Big 10?
so
It's
diodes.
all diodes.
So let's talk about a couple terms. What is a diode? The diode is a device that allows current to flow. A device that allows current to flow in one direction but stops the flow in the other, sort of, because there's different types, but that's the main type. But stops the flow in the opposite direction. Like a check valve. Oh, I did write that.
I'll put sort of.
Yeah, we can sort of. My favorite thing there, sort of. I don't know, modifier. I love you, sort of.
You can say so many words.
Depend on the day.
Yeah. Let's see. And electrical check valve. So again, now I've used hydraulic stuff, and now I have to explain that. So in a check valve in hydraulics, you have a tube. Why not make it big enough to see? There we go. And a check valve would kind of like have a swinging door, maybe like a block that's right here. So you can see that water or fluid would easily flow in this direction because it would swing the door open. But if you tried to do it this way, it would just lock the door closed and nothing would get through. So it's basically that, but for electricity.
Like a gas tank.
A gas tank?
When you put your gas in, it's a check valve. It only goes in one way, right? There's a little shield.
You ever heard of an Oklahoma credit card?
I don't know. I lived in Oklahoma, so there's a couple.
Really? That's where you put the. That's where you put the thing in. You siphon it out, and your gas comes out the gas can into somebody else's.
I mean, you can bypass any check valve.
All right. So, it's considered solid state. Solid state. Solid state is a device which solid material is used to control electric currents. So a device in which solid material is used to control electronic currents. Control electric currents. Electric currents. All right, semiconductor theory. I don't want to oversell it. It's my favorite video. Yeah, there is. Uh-oh, there's no pin there. Okay. Let me see here. We got this. That's fine. Take it down. Bring this up. This. Slideshow. Go ahead. This guy's cool.
In this phone, there are nearly 100 million transistors.
A bad start. But at least I know how to troubleshoot it.
It's still muted.
Huh?
It's still muted.
Well,
It's funny. It's only muted here. When you watch it online, there's actually a audio.